Okay, so this is where we left off. We defined sequential games and so on, and we looked at some simple sequential games like business proposals. So we'll be solving the first one, chess. Who plays chess? A lot of people. Okay. Okay, so before that, somebody pointed out a mistake, so I will just correct it. That this game, which is shown here, is not the same as this one. Okay, uh, because uh, because of my mistake. Obviously, I mean I just copied it from textbook without realizing that. I mean the author wanted to illustrate a point that this preference order could be different from this monetary values. That's what he wanted to illustrate. So I could have, for example, if I'm red, I may be preferring I don't know, O1 for whatever reason. Okay, maybe there is some reason. So for example, this and this one are different. For example, in this one, the equilibrium is this one, and if you take that these values actually represent the represent the preference order, then this is actually the equilibrium. Okay, just I mean you can easily work out that. Okay, is that clear? All about preference orders. So what about chess? So chess seems to be, how do we solve chess? It's a sequential game just like this. This is where we, okay, solve chess. Player 1, who is player 1? White? Oh, you're, okay. How many moves you have? How many arrows should I draw? No. Who is the first to figure out? Yeah.
20.
20, right?
Yeah.
2 pawn moves and then I think
4 knight.
20. Okay, what about the second player? Black. Again 20, right? What about the third one? Okay. So hopefully you can write that diagram, and where should you go? You should go all the way down. Okay. How many nodes will be there? Terminal nodes. Can easily see that this will explode, right? So luckily nobody has solved it, and don't solve it, please. Okay. So we have our world champion. So lesson: if you want to enjoy life and play games, don't solve games. Okay. All right. So he's from Chennai. I mean, hope I know all of you know probably. Okay. All right. Youngest world champion. Okay, so let's move on, and then we are not going to talk about dynamic this kind of games any further. We will actually dwell further into the same stuff, but more involved. Okay, okay. So this is a game. You don't have to play it, but you should tell me your preference. Okay, so the game is the following: 2 persons again, our row player and column player. You can put some bet like simultaneously. Okay, you show 100 or 200 note together. Okay, and then you see that now there is a difference. Okay, the difference is that if I am person 1, if I put 100 and the other put 100, okay, we have put equal. So I will get his money with half the probability, and it's basically a tie break. Okay, I will toss a coin, and if it is falls heads, then I will get his 100. Otherwise, he will get my 100. Okay. So similarly, if 200, then I will get his 200 with probability half, and he will get my 200 with probability half. Okay. What about if I play 200 and he play 100? Then obviously I will get. I am the winner. I will get the money. Okay. I will get 100 from him, and if I am 100, he is 200, then he will get my 100. Okay. That's the game basically. So don't worry about the game. What I wanted to tell you, what I wanted to think about is that, okay, so which one do you prefer? If you are, let's say, person 1. So I have separated out, O1, O2, O3, O4. This represents the outcome. If you are person 1, which one you will prefer? O4 or, yeah, O4, okay. Right, okay, hold on to that, O4, okay. And if you are person 2, you will be probably O3, right? Okay. No, but how did you rank these ones? Okay, so that's what I wanted. Yeah, but here, for example, also there is a so forget about O3 and O4. How did you rank between these two? That's a fundamental question. Okay. Okay. Suppose O3 and O4 settle. Okay, this is quite easy to figure out. But let's see which one do we prefer. Okay. Strictly speaking, I will prefer which one? O5 if I am person 1, right? Okay. Compared to O1, that's correct. But you see that this is probabilistic. If I take this as, obviously there's going to be some outcome out of this and some outcome of this. So which one you will prefer to have? That's a kind of question we are going to have. So making outcomes probabilistic. So the difference is that here the outcome itself, this for example, this cell is not very certain what I will get out of it. It is a probabilistic event. Okay. So how do you rank between these two? Okay. So we will conduct a social experiment, a well-known one. So this I have written the same thing. Let's see. Okay, I'm offering you this choice. Okay. You will earn 50 lakh with. I'm going to toss a coin. If it falls head, you will get 50 lakh. Okay, and if it lands on tail, you will get half. Sorry, 0. Okay, correct. Would you take this from me or this proposal from me? Second one, definitely. Why?
There is no risk associated.
There is no risk in some. Okay, that's a nice way of putting it. So you will be preferring this one to this one, right? Oh. No, only one. I mean, I don't have no money. I don't even have this, but let's imagine that. If it is, you said something. If it is iterative. Okay. Why? That's not that easy. I mean, you have a finite lifetime, and then how many iterations you need that. In this case, yeah, fairly you will quickly earn 50 lakhs, right? I mean, you don't have any cost, you just have to. Okay, very good. Okay. So depending upon that, so anybody prefers this one, L1 to L2? Okay. So what is between L1 and L2? If you see that, I mean, if you compute the the expectation value, then they are the same, right? They are the same. But then depending upon whatever you said, we can have 3 different things. Okay. One is risk averse. I hope all of you kind of showed risk aversion here. Risk aversion basically means that somebody who prefers getting the expected value of this one for certain than playing this one. Okay. I would like to, you just give me the expectation value of this for probability 1. I'm not going to play it. That kind of a person is risk averse. That kind of an agent is risk averse agent. Averse agent. Okay. What about risk loving? The opposite. Okay. A person who prefers to playing this lottery compared to getting the expected value for certain is called risk loving. You might think that, I mean, are we going to be risk averse in all kind of circumstances?
No, Sashi, I mean, strictly speaking, risk averse persons would even go for outcome which is less than P of L1.
Yeah, maybe, yes. Yeah.
So, suppose we say instead of 25 lakh, 15 lakh.
You take it, I think.
Risk averse person will still go for that.
Still go. That's probably. Okay, then how do I define? Let's see. Okay. So risk averse and risk loving, and there is this risk neutral who will consider getting this one and this one. There is kind of neutral between these two agents. Okay. 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 Whom do you think most people are belong to which category? That's not quite certain. I mean, in this case, maybe yes. If I change it, maybe if I put instead of 50 lakh, let's say I put something else here, maybe very big amount here. I don't know. Maybe I can entice you to be risk loving in some cases, maybe. But which one is least likely to be the case? What is that? Or risk neutral? I don't know. I mean, risk neutral. Okay. Okay, so is that least likely? Okay, so we are going to assume that people are risk neutral. So why? at least for the moment, take it that because you can do math with it. Is that a reason? I don't know. But let's. So this kind of things is kind of well known. I mean, so what is the problem with assuming that agents are risk averse or risk level? Okay. So one problem is that, so this is again, I ask you to compare, this is a kind of famous social experiment. So which one do you prefer, okay? A or B, okay? 5 lakh you are getting with this probability, 0 with this one. 1 lakh with probability 90 by 100 and 0 with, I think this should be easy. Which one do you prefer? Anyway, how many A's? So there are, okay, good. So what about this one? Okay, hold on. 5 lakh with 8900, 1 lakh with 10 by 100 and 0 with 1 by 100. But I am going to get D with just 1 lakh with a certain. Okay, which one? C. How many C's? Any D? You D. Oh, why?
Oh, maybe I will get 1 lesson.
You're happy with life. Good. Okay. So the problem is that, I mean, if you, for example, if you're assuming risk neutrality, then so obviously usual answer is A greater than B, and usual answer is D greater than C. Usual answer means that in the experiment, social experiment, this is well known. It's called the Allais paradox. Okay. Why it's a paradox? Did you face any paradox in choosing? Well, the reason is that if you prefer A to B in this one, then you can show that you should have preferred D to C. If you are a risk neutral, expected utility or expected payoff maximizer in such sense. No, because you can figure out that in this case the expected payoff of oh, did I miss it? I think I kind of reversed it. I said usual answer is D greater than C, right? No, I think it's the other way around. Maybe I goofed up. Yeah, you can figure it out. I mean, so the thing is that the paradox is that that's incompatible with the what is that expected. So here is the thing. Okay, don't take it too seriously. I mean, if I'm a physicist, for example, if I make a bad assumption, if I make a theory with an assumption which is very kind of does not, what do you call it? Okay, if you make an assumption in physics, which is outrageous, flat earth, what do you call it? Bad assumption, right? You will say that no, that's bad assumption. Okay. Economists call it either a paradox or a dilemma or something. Okay. So anyway, this is a paradox. Okay. So if you were actually kind of risk neutral in some sense, then you should have. Let's not use that word, but if you were maximizing the expected payoff, expected money, for example, then should be the other way around. That's the lesson. Okay. So the thing is that why do we want that property? If that property is not there, then it's slightly difficult to.
Excuse me, sir. How risk neutral wouldn't choose? Like in the last example, we just chose based on expectation value.
Which one?
Here, C expectation value is greater than D and A is greater than B. We chose exactly that.
Oh, you choose exactly that.
Yeah.
No. So. No. What do you mean? So I think I kind of reversed this one. What is expectation value? Now I have to be careful. What is the expectation value of this one? 4 point. Is greater than what, right? Yes, now paradox for me. Okay, no. But I cannot do computation now. But I will figure it out. Okay. Most probably I goofed up some numbers or. But I hope you got the point, right? Okay, you will find some. Okay. Okay, so here is the thing. If I want to do that same thing with this one, Okay, what I'm going to do is that I will say that my expected outcome out of this is basically 0 because I'm going to get 100 or lose 100. Okay, and same with the other person. So I can actually transfer this to again numbers and all my nice properties will be there, like transitivity and so on. Okay, that's the basic idea. Okay, if you are not assuming that, then you will be in trouble because you can show that. For example, the transitivity. You cannot. The same person cannot rank the two outcomes in a consistent way. Okay. Under some circumstances, he will be say that I will prefer A to B, and then under some other circumstances, it will be opposite. Okay. That's the problem. Okay. So so under that assumption, I can now easily rank them. Okay. So a risk neutral player, I can say that I prefer O3 and I don't care between O4, O1 and O2. Okay, that's the idea. Okay. Okay, so again, just like in the first session, what we basically did is that we went from outcomes to numbers. Okay, this time the difference is that instead of putting some numbers, we are putting the expected value of that.
In one of those is losing,
Which one?
O3. No, in O4.
O4, yeah. He will be losing 100. Yeah, that's correct.
Should be minus.
Minus one. This one? Okay. I mean, yeah. Okay. 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 So the basic point is that I can make outcomes probabilistic. That's the basic idea. Okay. I can do that the same thing with strategies as well. So this is the key difference from the previous session, that so far we were considering just the case that I will either play head or I will play tails. Okay. Now you have the possibility that I can. Let's consider the possibility that I can play heads with some probability and tails with the remaining probability. Okay. So I'm making my strategies also probabilistic. Okay. Okay. And then basically instead of payoffs, I'm going to I will work under the condition that I'm going to maximize my expected payoff out of this. Okay. Considering this probabilistic setup, and assume that players are interested in maximizing the expected payoff. So that the only difference from the previous scenario is that now we are allowing probabilistic strategies between this one and this one, and then you want to maximize this. So what happens then if you want to maximize it? Okay, so I was just going through, are there any, so you will see that this is kind of a big debated topic in economics. He will probably able to tell more about it in the sense of whether actually what is the best model to model for human beings in these kind of situations, risk neutral, risk loving, what is the evidence for and what is against that, and so on. Now okay, so we do. So let me ask this: right now, which species has the highest intelligence on Earth? Human beings or somebody else? At least there is something coming up, right? What is it? AI. Do AI play games? They can. I mean, Alpha. Okay, those kind of games, but they can also involve in slightly different games. Can they involve in chicken kind of games? Maybe autonomous drivers, for example, if they decided to play chicken with the oncoming traffic, you will be in trouble. Okay. So I'm not kidding. I mean, you will see that recent works where you actually try to figure out what will happen. So I would say that for example, you just read this line: in hybrid human AI driving system, it is necessary to limit large deviations in reward resulting from car crashes. So if you are, if AI is going to maximize the expected payoff, under some circumstances there will be big trouble. That's the underlying message. Okay. Imagine that a group of and that's very much possible, right? I mean, for example, if AI starts to make decisions among themselves and so on, that's quite a possibility, very vaguely. Okay, I'm not saying anything concrete. Okay, and you see that it's very so that they claim that okay, this appeared where in so this is in PNAs. Large language models like the GPT, if they can actually if you ask them to make decisions and so on, they are mostly rational and so on. The performance is affected by the way, but then what happens then? Okay, do they actually play according to the economic rational player, or do they behave like ordinary human beings like us? Okay, in a risk averse manner, risk loving manner, risk neutral manner, and so on. Okay, very contemporary. I mean, I just picked up some random examples, and if you are a bio person, then there are you can read the title. Comparative economics, how studying other primates helps us better understand the evolution of our own economic decision making and so on. These are well, this comes from an issue in RSPB, Royal Society B, which is completely dedicated to this topic. Okay, so if you're interested, you can have a look at it. Okay. Okay, and the fourth random paper, you can just read the title. I don't even know what that is, but I heard that this is some worm which you love. Many so say that they do this. eLife recent. Okay, I just picked up 4 recent papers randomly, so which might be of gives interesting directions to think about. That's all. Okay, all right.
So you're basically saying that economic rationality is not something exclusive. Is that
Exclusively?
human?
Yes.
Other animal species and AI are also spontaneously.
Yes, animals probably in a different way. I will talk about it because that's the whole topic of evolutionary game theory. But certainly AI, there is, for example, AI don't have these kind of biological restrictions. I believe. I mean, neural systems where you fear about punishment more compared to reward and so on. But it can emerge new properties in itself, I believe, and people have seen that. Again, this is completely, speculating and you're just thinking about, futuristic stuff. Okay, but I hope that that's something interesting.
Actually, this question is an important point because my understanding is that most humans don't behave rationally, or at least in terms of economic rationality.
Yeah.
So the fact that neural networks trained using such
But
non-rational agents actually behave.
for example, GPT takes all the literature, economics literature. You have all the economics literature.
For the economics literature, actually.
Probably learns from economics literature and game theory literature. I don't know. Is it a big thing yet in economics? I don't know. Not probably. Not.
What?
You were whether AI is rational or AI behaves like usual game theory agents. So, have you come across those
Generally,
discussions?
people think of it in a with a different framing, I suppose, which is that. So, for example, you do not usually talk about economic rationality per se. There is nothing particularly economic about
Okay.
it. The point of rationality is that actually, so this has also been often said that rationality is a bad choice of word. It should be more like consistency. We set up an objective function, set up budget constraints, and then allow a consistent choice program to make the decision. So technically, it should be more like a machine which is supposed to solve that problem, come up with the answer. The question was whether humans mimic it or not. So that way, one thing that is known very well is that we are very bad at combinatorial problems, figuring out chess moves, go moves, and so on. So there, the fact that it fits humans, it's not particularly surprising. and changing the behavior in terms of, let's say, capturing propensity to punish someone else, so on. These things can be actually modeled very nicely and easily by defining objective functions accordingly, or the cost functions accordingly. So you can simply say that you have to punish in order to reduce your own cost. So then it just becomes a cost minimization problem. So then technically this can be replicated very easily. In fact, it's almost like humans replicate that what the machines do very well, which is the other way of looking at it.
Okay.
I actually do not know what does it mean that this title
Yes,
is maximizing economic utility. Is it like utility out of consumption? Is that what is being described?
No, I don't know. I mean, as I said, I mean, just randomly picked 4 reasons.
Okay.
That's in different fields. Okay, one has to read carefully. Okay. The purpose is just to show that it's contemporary in some sense. Okay. Okay. All right. So let's go forward. Yeah.
Game with probabilistic strategies.
Yeah.
With fixed payoff.
Probabilistic strategies with this. Yeah. For example, this one. Correct.
Is it analogous to having fixed strategies but probabilistic payoffs?
Fixed.
I mean, could there be constraints under which these were similar? So making noisy decisions is the same as being rewarded in a noisy way.
No, that's a. Can I?
Yeah.
So that would be a different setup where you are saying that the way to think about probabilistic payoff is that there are multiple games and you are choosing some game with some probability. Each of the game has a fixed payoff. You are just choosing between games. That changes the nature of the game, because then you are changing the strategy space as well. Then you are not choosing from the within the strategy space within the same game. The part of the game itself also becomes the nature of the game itself becomes your strategy. Then you are changing the nature of the game.
Okay, so you can consider several such games,
Yeah.
right? But then this comes.
These numbers are different, and
distribution.
with some probability you can choose between them. But that's a different class of games.
No, but
Would there be constraints under which these two are equivalent? Like some
Which two are equivalent?
having probabilistic payoff is
So-
equivalent to having probabilistic strategy.
so you say under what conditions these can be considered equivalent in some sense?
No, this can still be thought of. So you can take all of these games differently, put them all up in a larger game matrix, where each of the subsets will be this game. So your strategy then would not be, let's say, heads or tails. It would be game 1 heads tails, game 2 heads tails, game 3 heads tails, and so on. Similarly for the other person. So you can then define a probabilistic strategy on that larger game,
So he's asking.
taking that super game as given. So there's still the same solution concept will work there.
So they will give the same P basically, P star. Is that what? So if you choose from several games, some of them heads, some of them tails, you have a fraction of heads, fraction of tails. Will that fraction will be the same as the solution of this one? I think that's what you are asking.
No, there the game is different. Why would the solutions be identical? There you are also choosing the game. So it may or may not, depending on what are the different payoffs that are given.
So the only difference from the previous one is that you still have players, you still have all these outcomes, but the only difference is that now we are actually allowing probabilistic choices between heads and tails. I can write the notation, but I'm not going to do it. Let's not worry about that. But then it's just an extension of the previous one. I will write it at some point whenever I require it. But then this is the what the kind of punchline of the game theory stuff. Okay, this we have seen earlier, right? A strategy profile such that no player can increase their payoff. That's the definition of Nash equilibrium. Okay, and what we found is that in some games they do exist, some games they don't exist, and so on. And here is the punchline. Okay, in what Nash proved basically is that forget about this technical term. Every reduced game in strategic form basically means that a game like this will have and each agent having a finite set of pure strategy has at least one Nash equilibrium, okay, at least one, okay. So you might see that this is something reasonably big enough, okay. One can think of this as, okay, we have at least a very solid concept which has solution for all problems in some sense, okay. That's the key idea, okay. What happened to further that I will describe later, but for the moment now we are allowing mixed strategies, and there is equilibrium is guaranteed. Okay, how do we find them? That's a very practical question. We will find them. Okay, this one is your room cleaning example from the first one. Okay, do you realize this one? Okay, you clean 2 and so on. Okay, what is the Nash equilibrium in this one? You figured out. This one is 1. Okay, right? Remember this from the first class. So you see that. So the one thing is that you in this one there is only one Nash equilibrium. Okay. How do I know that? For example, I can perform. I just delete all the strictly dominated strategies, and I will end up with one particular choice only. If I am player 1, no matter what the other person do, I will not clean my room. That's the kind of argument. Okay. So this one does not have any mixed strategy Nash equilibrium. You also see so that why the prisoners, why the game theorist and all the other people are so obsessed with the problem of why people can't do 2. Okay, so yesterday we were talking about under what conditions we can expect Nash equilibrium and so on, right? You have to think in the other shoes and so on. But if you consider this one, do you require any of that? If you are person 1, do you require anything? Do you want to know anything about person 2 for playing don't clean? Okay, no. So this one, in some sense, you don't require any mutual, the common knowledge of rationality or anything like that. So it's so somebody said that it's a tough nut to crack. I mean, in the sense that it's a very solid dilemma. Okay, very hard to get rid of. Okay, you will have to really twist and turn to actually argue that people do cooperate in this setting. Okay, but there is no mixed strategy Nash equilibrium in this case. What about this one? This one we know that there is no pure strategy Nash equilibrium. This is the tossing a coin game, heads or tail, I win. Okay, if it is opposite, you win. Okay, that's a game. Okay, so this does have a mixed strategy Nash equilibrium. Let's see how do we find out. Okay, we can find out in different ways. At least in this case, they are all equivalent depending upon your taste and so on. I mean, so a very easy way is actually to draw what is known as a best response curve. Okay, so what do I mean by that? So in this case, this is how I denote a strategy profile. Okay, so sigma is a strategy profile, which means that the first bracket is for player 1 and the second one is for player 2. The first bracket basically means that the first player plays heads with probability p and tails with probability 1 minus p. And for the other one, I have chosen the variables q and 1 minus q. So all you have to do is write the expected payoff, okay, of player 1. If you are player 1, what is your expected payoff? So expected payoff of player 1. Let's call it W1. How do I calculate it? Well, you know now that with what probabilities each of these outcomes will happen, right? What is the probability that I will be playing heads and he will be playing heads? I am playing heads with probability p and he is playing it with q, and we are independently doing it. Okay, PQ. So that's pq. Okay, so if it is pq, I will get 1. So 1 times PQ and all the other combinations. If I am choosing heads with probability P, he is choosing tails with probability 1 minus Q, then 0. So I don't have to write it. Here also it is 0. The only other instance in which I will get a payoff is this one, and that happens with probability tail. Okay, what is that? Yeah, it's 1 minus p, 1 minus q. Okay, and I am getting 1. Likewise, I can do for player 2. Can you write it? Well, player 2 gets a payoff only here, and those things happens with probability p and 1 minus q. This one, p and 1 minus q, and 1 minus p and q. Okay. Okay. So what can I do? So what I can do is that if I am player 1, if you are player 1, all you can do is that vary p, right? Okay. So what you can do is that you can draw this one. Okay. What is this? This is best replies of person 1 and person 2. Okay. So if you are player 1, basically I am doing the following. Red is player 1. Okay. This is q and this is p. For various values of q, what is my best response? What is the value of p which will maximize my payoff? Okay. So for q equal to 0, what is the value of p which will maximize my payoff? If q is 0, then he is playing tails. Then it's better for me to play tails also. So p should be 0. So that's my best response. Okay. So when player 2 is employing a particular value of q, okay, all along here, my best response is to have a p which is equal to 0. Okay, and from here onwards, my best response is this one. Okay, that's why this red curve looks like that. Is that okay? How do I figure out what value of p will maximize this? So you do that in whatever way you would like. I mean, you can. Okay. So this is the best response curve for player 1. Do the same for player 2. Okay. Now I have to look like this. If I am player 2, okay, for various values of p, what is my best response? For example, if p is 1, I will be choosing 0. Remember that this my payoff is better if you have a different choice and so on. So it looks like this. Okay. So what is the mixed strategy Nash equilibrium in this one? Well, it is basically q and p wherever this curve crosses. Why? Because that's the only point where they are the best responses of each other. Okay. Basically, that's a definition of Nash equilibrium. If that guy is choosing this q, I will be choosing this p, but then his best response is something else and so on. Okay. So
What is the meaning of pure in which strategy then?
a pure basically means that p is 0 or 1. Basically, I'm playing. I'm only allowed to choose either heads or tails. So mixed basically means that mixing is allowed between them.
Like
Probably. So how do you do that in practice? You just toss a coin and. So this is that value. What is that value? You can easily guess what will be that value. If you were playing this game, with what probability you will choose heads? Is that the Sita bro? I just have to call. Yeah. Okay. So if you were playing something like this, what is the probability with which you will play? Will you choose anything different from half? Intuitively, if suppose you are going to choose something different from half, then my best response will be one of those pure strategies. Okay? Because you are maximizing expected payoff, right? If I suspect that you are, if I am person 1, you are going to play heads with a slightly better probability, then what should I do? So, well, I should play definitely heads. Okay. That's maximizes my payoff. Okay. So this is the only mutually consistent choice in the sense of Nash equilibrium that is possible. Okay. So in this game, P equal to half, Q equal to half is the Nash equilibrium. Okay. The other example easily you can, without even doing, you can figure out rock paper scissors. What is optimum strategy in rock paper scissors? What could be? Yeah. 1/3, right? 1/3 should be 1/3. You can think of it various ways. If you have a different than 1/3, then of course there is a pattern in whatever you are doing. The other guy can exploit it. Not a pattern. I mean, there is a higher chance that you will be playing, let's say, rock, then the other guy will play which one? Rock is beaten by paper. Yes. Okay. Cool. Okay. This is one way of figuring out. There is a very cheap way of doing this. Cheap in the sense that it's okay, but what you have to do is simply maximize this with respect to, this is my payoff. I'm going to maximize this with respect to P, right? So let's do that. Differentiate that with respect to P. What will I get? I will get Q, and okay, I have to differentiate with respect to P, which will give me minus 1 minus Q. I hope that is correct. Correct? Correct. Maximize, so equal to 0. What is the value you will get? Q equal to half, and I don't have to do the other way. I mean, you will get P equal to half. Why this is cheap? Because you have to be careful, because I am maximizing a function. Okay, I can equate it to 0, but make sure that this is actually the maximum. Okay, and also you might end up with getting some value outside the interval 0 to 1. Q is restricted to 0 to 1, so that's not a problem. Okay.
So I did not get
Yeah.
Lay heads, if I'm person 1 and lay heads, the probability greater than half.
If you are person 1, okay, let's see. So I'm the green guy. Okay, okay. You are going to do what?
More than half. The lay heads.
More than half? Yeah. Then my expected payoff is better if I play Q1. That's what it means. Okay. Comfortable with this way of doing? You can draw the best response replies and just look at where they meet. Or if you just want to use maximization, you can do the calculus and figure it out. Okay. There is also a third way, which I will tell you. But before that, just to quickly go through, we have done this stag hunt. There are two pure strategy Nash equilibria, right? This one and this one. Okay. If I draw the best response curve, I will also find that there is a third one. Okay. In this case, it is playing Q with 1/3 and P with 1/3. Okay. So agent person 1 will play stag with probability 1/3, and the other guy will play stag with 1/3. Okay. That's also a Nash equilibrium. So earlier we found this one and this one. Okay. So whenever these curves meet, that corresponds to a Nash equilibrium. This one is a Nash equilibrium. This one, there is also a third one. Okay. What is the third way? The third way is that you will see something peculiar from these two things, right? When suppose I am person 1, okay, and person 2 is playing her Nash equilibrium probability, which is this one, right? Right, this one. Okay, if you are person 1, is your payoff going to change if I play with any P? Suppose he is playing here, you see that this is kind of vertical, right? I mean, so no matter what P I choose, I will be getting the same payoff, right? Is that clear? Okay. Likewise, the same for the other player also. If I am playing my Nash strategy, which is P star, okay, it's immaterial that whether he plays any of these values, because this, you see that it's just vertically fixed up, okay, right? That's called principle of indifference. We can use it. So I have stated this formally here, that one can use it to find we will use it, okay, in a moment. Very easy. So at a mixed strategy Nash equilibrium, an individual player will get the same payoff if she uses any of the pure strategies. Okay. Now assuming that others continue there, okay, that's what is written here. But this is only a necessary condition. For a two-player game, it's also a sufficient one. Visually, we can easily see why in a moment. Yeah.
Explain the notation.
Okay. This is why. I mean, sorry. I had something. So this you will see a lot. So basically, a notation like this, it basically means that payoff of player I. If I play strategy, whatever S1 my strategy, and this notation basically means that all the other players. So minus I basically means that all the other players. Okay. So read it in words. Payoff of player I, when player I plays the strategy SI, pure strategy SI, and everybody else using their mixing strategy. So S is for pure, sigma is for mixed strategy. Okay. What is the star correspond to? Nash equilibrium. Okay. So try that again. Payoff of player I, when player I plays the pure strategy SI, and everybody else playing their mixed Nash strategy. Okay. That is the same as if I change from SI to any other pure strategy, SI prime, and all the other players are using the same strategy. They are the same, basically. That's what this statement means.
So minus I?
Oh, minus I means I apart from I, everybody else. Okay. Okay. So how do we use it to find the equilibrium? Okay. So this is again a game, hawk-dove game. We figured out that there are two Nash equilibria in this case in pure strategies, where they anti-coordinate, right? Defect, cooperate, cooperate, defect. That's what these 2 points correspond. So what I have drawn is again the best response. This is the Nash equilibrium. I can also find this by the principle of indifference. How do I find it? Okay, in the following way. What does it, principle of indifference, what does it say? It says that if player 2 is playing her equilibrium strategy, let's call it Q star, okay. If I play C or if I play D, I will get the same payoff, okay. That statement is the principle of indifference, okay. So how do I use it? What is my payoff when I am playing C? Assuming that the other person is playing a probability Q. So if I am playing C, I am here, right? So if he is playing Q, I will get my payoff is basically 4Q. Did I? No, this is correct. This should be correct. This should be correct. Yeah, so let's write it. So what is my payoff when I play C and the other guys? So that's basically 2 times, I will get a 2 with probability Q, and I will get a, no, goofed up again, no, or is it the other way around? If I play, okay, this is the other way around, okay, sorry. 2Q plus 1, okay, this is, I cannot write it here, but this is D and this is C, okay. All right. So if I play C, what is my expected payoff? He is playing with probability Q. So with probability Q, I will get a 2, right? So I will get 2Q plus 1 times what? 1 minus Q. So 1 minus Q, that is 2q plus 1 minus q, which is q plus 1. Okay. So read this as C. So when I am playing C, I will get q plus 1. And when I am playing D, I will get what? With probability q, I will get 4. And with the remaining probability, I will get 0. Okay. So you draw that. Basically, the principle of indifference states that the point where they meet is the Nash equilibrium. So you can simply equate it. Okay, 4q equal to q plus 1. The solution is q 1 by 3. That's another way of finding the Nash strategy, mixed Nash strategy. Okay. Is that okay? All right. Let's skip that. You can extend this to 3-player game, but remember what I told you, that the principle of indifference is a what is that? It's a necessary condition. It's not a sufficient condition. You can easily see this because if you have 3 players, okay, and a pair of 2 players and 3 strategies, for example. So suppose you are person 1. Okay. If I am playing A, then my expected payoff is what? 3 times q, right? That's what is plotted. Where is it? This one, red one. Okay, 3q. If I am playing B, what is my expected payoff? 0 times q, 3 times 1 minus q. That is plotted this one. Okay, and the last one, when I am playing C, my payoff is a constant. That is plotted here. So the principle of indifference, if you want to apply here, you can, but then note that it could be either one or either this one or this one. Okay, you see the problem. If there are 3 curves, then this can happen, and so you have to be careful. One of them will be the Nash equilibrium. You have to figure out which one. That you can do. Okay. So what I mean to say is that for a 2-player game, principle of indifference solves it completely, but for this kind of a situation, so 2-player, 2 strategies, it's okay, but 2-player, more strategies, you will have to be a little bit careful. Okay. So if you want to figure out the probabilistic Nash strategy, either draw best response curves or do something like this, or do this principle of indifference, but these are only possible for low number of players. If you have a game with a lot of players, lot of strategies, you will have to resort to some kind of an algorithmic method. Okay, that's okay. So the uptake is that what is a probabilistic Nash equilibrium means, and then how do you find them in simple games? Okay, so so this is the end of kind of the formal stuff. So let's think about it. So we have an idea which is quite robust. Okay, to interactive decision problems. Equilibrium is guaranteed to exist, right? That's very nice property. Gives an analytical handle to solve strategic interaction. That's very good. Okay, a benchmark for comparison. Okay, you can compare what you see in real life or in some other situation with what is the optimal given by the Nash. Okay, but you also see that there are a lot of problems. Okay, so what are the problems? There are many. The first one is too many equilibria for a game. It's like saying that there are a lot of answers for a problem. Okay. Now, historically, when game theory was developed in 1950s and so on, the highest hope was that Nash equilibria are too many, but if you apply some on top of it some other idea, then hopefully you will end up with a unique answer. Okay. And if you are taking a standard course in game theory, you will go along this line a lot. For example, he was mentioning that sub-game perfection, 100 other ideas, which what happened is that hope was not that hope was kind of didn't materialize. By 1980s and so on, it was very clear that you are not going to have a single principle which will give you a unique answer, unfortunately. Okay. So equilibrium selection problem, this is something which you will likely to study a lot if you are taking a standard course, but again probably not very useful if you are in some other stream. Okay, and you can argue that if you want to play Nash equilibrium strategies, you are demanding very high cognitive abilities from the players. Okay, you know that what he is thinking, and you know that what he is thinking about you, and all that. It's a common knowledge of rationality and so on. Okay, very high things. And dilemmas, as in PD, were the obvious kind of dilemmas. People cooperate. Animals cooperate, but game theorists don't. So those dilemmas are a big problem. Now you can circumvent that by various methods. Okay, you can include, you can say that the game is indefinite. You can include some cheap talk between the players before the game, and so there are standard ways of explaining out these kind of things. But it still remains that the dilemmas remain. That's one way of looking at it. And needless to say, it's often at variance with observations and experiments. Okay, you can either argue or against it, mostly against it, I guess. Okay, and the bigger problem in this kind of pairs is okay, what do you mean by a mixed strategy solution? Okay, very hard to interpret. Okay, suppose we are engaged in a one-shot game. How do I even figure out that you are actually mixing? Observed action cannot tell you about agent mixing. How do you figure out that some person is okay? We play a stag hunt. Okay, just one shot. How do you figure out that I'm mixing? Remember, all I'm defined the equilibrium for one-shot games. Okay, you can interpret it in another context. Very unstable basically means that a slight deviation from that mixed strategy will kind of drive you away, and payoffs are often inferior also. For example, if you take this game, at the Nash equilibrium, the payoff is 4/3. Expected payoff of each player is 4/3. And you can easily see that this is better than that. Okay, and so. Okay. So all these problems. So you might think that okay, so don't take it from me, but take it from some true blue game theorist / economist. This is just read it. Different game theorists propose so many different rationality definitions that the available set of refinements of Nash equilibrium become embarrassingly large. Eventually, almost any Nash equilibria could be justified in terms of someone or other's refinement. As a consequence, a new period of disillusionment with game theory seemed inevitable by the late 1980s. Okay. Okay. So in the remaining 5 minutes, I am going to talk about that disillusionment. Do you know what that is? Okay. Seems that the rescue comes from biology, which is Darwinian evolution. Okay. Okay, agents may not be rational, you may not be rational, me may not be rational, but seems like in a variety of conditions, natural selection is rational. So what do I mean by that? I will just describe it in 5 minutes, and then we will wind up. Okay. So there was a whole new talk, but then I don't have time. Yeah, okay. So remember that whatever we described is a very static idea, right? Even the extensive dynamic game, you just solve it and play it. Okay, there is nothing dynamic in that sense about it. It's a very, very static idea. What happened in 1972 is that these two gentlemen, that time, Smith and Price, introduced some idea about evolutionary stable strategy. Okay. Just think about it as a special Nash equilibria. Okay, it picked off after 1980s by after the book by Smith on the topic. You can see that by that time George Price was dead. Are there any people who study evolutionary biology here? So you will hear about this guy a lot. Have you heard about Price? So read about it. Okay, it's a very tragic life. If I had time, I would have. He committed suicide. Do you know why? Because he tried to kind of disprove games. No, because you know the selfish gene theory. It's all right, and you are related. You should help your relatives because they are related. Okay, that kind of disturbed him too much. Not the book. I mean, the idea of the gene. Okay, disturbed him very much. And the story is that he wanted to kind of disprove how can that happen, and he started donating everything he has to all the strangers, and in the end, was a very tragic end. Okay, just read about his life if you want to have some entertaining stuff. Okay. Anyway, what is a big deal about it? It led to a dynamical consideration of equilibration in games. Okay, so I will very quickly tell you what that is. There are 3 changes. Okay, so we are going to do this very quickly. So please be please cooperative. Okay, in the sense that we are changing everything. Now, I'm going to play this game, hawk dove game, with all of you, or you are going to play against each other. But now there is a difference. Okay, the difference is that you don't have to think. Sit and relax. Okay, all you have to decide is, okay, your parents were belong to this category or this category. Okay, just some 2 genetic traits. Okay, aggressive, peaceful. Okay, quickly, who are the aggressors? No, it doesn't matter. Okay, one guy, one hawk. Okay, who are the peaceful guys? All the remaining ones. Okay, okay. So you are endowed with that gene. Okay, got it? This is a difference, right? So strategy does not come from a set. You are endowed with a strategy. Where does it come from? It comes from your genes. Okay. 2 strategies. Okay. Now it could be cultural inheritance, genetic inheritance. I can talk about cultural inheritance. What is your all kinds of inheritance. Okay. All right. Be careful. Who are the peaceful? So there is one hawk. Good. Okay. Interactions. Random pairwise interaction. Okay. Okay, I'm going to just mix it. We had a term for that, right? Mean field kind of thing. Okay, pairwise interact, and whenever pairwise interact, what will happen is that you will actually give this payoff and interpret this payoff as your progenies in some sense. Okay, cooperate. 2 children of the same gene. Okay, there is no gene mixing and so on. So this is like asexual reproduction. Okay, so that's what defect cooperation. The defector will have a very high. Okay, you can think of that defector will take a lot of resources so that he has a better chance of producing a lot more progenies. Okay, you got the gist of what I'm saying, right? So you pairwise interaction and then it will go off. Okay, quick question: where will the population end? Now I defined a very dynamic process, right? Correct? Assuming the population is large. And all these pairwise interaction, okay, bingo, you will end up in a Nash equilibrium. That's a rescue line for Nash equilibrium. Okay, so in the end, equilibrium, the state you are going to reach in the final, some proportion of hawks and some proportion of doves, that will correspond to a Nash equilibrium, a special Nash equilibrium, evolutionarily stable Nash strategy. So Sagar will tell more about that, but I hope you got the point. Okay. Now see what happened, that a static idea of equilibrium now became the fixed point of a dynamic process. Which process? An evolutionary process. I can define it very carefully. So which evolutionary process? So we just okay. Just to be fair, I mean, I told you that ESS itself is a Nash equilibrium, right? So there is no concept of time or reproduction in that in an explicit way. Okay, you have to build up an evolutionary dynamical interpretation. That's this. Okay, you start out with a large population involving all strategies, like half of them hawks, half of them doves, random pairwise interaction, reproduction based on payoffs. Okay. How do I do that? I can say copy the successful strategy, or I can, and the punchline is that the expected steady state will be an evolutionary stable strategy. Okay. Can we define such a dynamic process? I can do that either in the language of differential equations, that's replicator dynamics. The only thing you should know if you are an evolutionary game theorist is replicator dynamics. Okay. I will skip this and then I will end in 2 minutes.
The slides will be anyway up.
Yes.
But they
So
are up already.
yeah. So this is my, I think, my last slide, or penultimate slide. Okay. Okay. So from the static view, you now have a dynamic view, such that the dynamics will lead to the equilibrium. That's the view. Okay. Okay. So all the tools you have studied, you can use it. Difference equations, differential equations, the concept of a stable point, stable fixed point by theta bra. Okay, all those points will be of interest, and you can study often interested. You are often interested in the large scale properties, and all those questions like this will have some elements of game theory. Okay, so I will end with this slide that this is what we started with, that you have this hierarchy of disciplines, and I said that here you have interaction between entities, and now we have what is known as strategic interaction between entities, and basically we were looking at this problem, and then how do we incorporate that into various theories. Okay, so for example, you studied yesterday Markov chain dynamics, right? State from state to state, W1, 2. So in this kind of a context, it will become a Markov chain dynamics depending upon the payoffs you receive. So each of your W elements will become a function of the payoffs. Okay, or each of the fraction of things in the next generation will become a function of payoffs and so on. Okay, so dynamics will start to depend upon payoffs, and what are the consequences of that? That's what you can address. Okay, okay. So I will finish. I'm sorry, 5 minutes. Done. Yes.
So you motivated this whole idea by saying that the usual refinements are not, particularly good for empirical analysis. So I'm just wondering how good is ESS, because I am aware of the solution concept. I don't think it's also particularly empirically verifiable.
May not be, because it has a lot of drawback. For example, as such, if you want to introduce something like mutation, which is essentially a part of evolution, then you are essentially introducing a new strategy. At least in this context, what we are saying is that you start with hawks and doves, where it will converge to.
I'm saying that you made this comment that ESS came to rescue.
Oh, no.
So,
okay. In the sense that you now have a dynamics which will lead to a Nash equilibrium. Rescue in some sense, in a very, what is that, metaphorical sense. That's
okay.
But there is also a dynamical systems framework that you put out in this book chapter. We showed that.
yes, I could have talked about it, but then again.
No, but we can put it up on the
So I can.
workshop page. So basically, using flow lines, so looking at this as a dynamical systems framework, we can see the phase space as basically the space of the mixed strategies. So let's say P is the probability that I will cooperate, and Q is the probability that the other player will cooperate. Then I can formulate all of it in terms of differential equations and see it as a dynamic.
No, that's fair, but that's
You're asking what is the empirical evidence for ESS. Right?
basically I'm saying that that's an unfair comparison, because the refinements are existence theorems. They are not dynamical systems to begin with, very deliberately.
Correct. Yes.
So therefore, you cannot expect dynamics to come out of it.
No, but it did came. That's why I said. I mean, unless, for example, you define ESS, and suppose that there is no evolutionary process which will lead to ESS, that will still remain as a very one more refinement.